Welcome to This Explainer. Have you ever read a massive medical headline and thought, okay, but how did they actually prove that? Well, it turns out it doesn't just happen in a test tube. It happens on paper through some incredibly rigorous statistical frameworks. Today, we're going to demystify the behind-the-scenes math that biostatisticians use to validate clinical claims. We're going to walk through the exact statistical decision tree researchers use to evaluate their data. Let's jump right in.
Here's our roadmap for today's explainer. We'll quickly move through 1. The null hypothesis, 2. Defining categorical data, 3. The chi-square framework, 4. The small sample problem, and finally, 5. Fisher's exact test.
All right, part 1, the null hypothesis.
We've got to start with the absolute bedrock of all clinical research. This is the baseline assumption investigators must attempt to disprove, and it happens before a single patient is even enrolled. You see, science is basically the ultimate skeptic. It begins by assuming a treatment does absolutely nothing, or that two variables are completely unrelated. This is the null hypothesis. It's defined right at the starting line, and the whole point of the research is to test it, to either accept or reject it. It's a super conservative approach, but it stops us from jumping to conclusions just because we really want a new drug to work.
So, let's make this concrete. Picture a medical student writing a retrospective cohort study on acute pancreatitis. Their null hypothesis has to state that paracetamol use has zero association with the disease. None whatsoever. Their alternative hypothesis, on the flip side, would be that there is a statistically significant link. By setting up this baseline, the researcher creates a mathematical hurdle. If the data later shows a significant association, great, they get to reject the null hypothesis. If not, they have to accept it.
Moving right along to step 2. Defining categorical data. This is where investigators hit their first major fork in the road. They have to correctly identify their data type, because this decision dictates every mathematical test they're allowed to use moving forward. There is a sharp fundamental contrast between continuous data and categorical data. If you're measuring things on a sliding scale, like average blood glucose or mean blood pressure, you've got continuous data. You'd use tools like a t-test or ANOVA for that. But if a study is bucketing patients into distinct, independent groups, like healthy versus not healthy, or developed an infection versus totally uninfected, we are officially in the realm of categorical data.
Think about a classic comparison, like looking at the presence or absence of a specific variable against a clinical outcome. A textbook example is comparing whether or not a patient uses tampons and cross-referencing that with whether they develop toxic shock syndrome. You aren't measuring an infinite scale here. You're looking at distinct yes or no values. You use it or you don't. You get sick or you don't. These are categorical values. And when we want to test for differences between percentages or proportions in these buckets, we have to travel down a very specific mathematical path.
Which brings us to part 3, the chi-square framework.
Okay, so you've established you're dealing with categorical data, and let's say you have a nice, large study population. Biostatisticians will standardly map these outcomes onto a contingency table, cross-tabulating independent events. Imagine a trial evaluating a brand new medication, drug X, against a placebo, while tracking if a disease is present or absent. The data neatly drops into these 4 specific cells in a 2x2 grid. This gives us our observed frequencies, the actual real-world numbers of what happened during the trial.
Now, how do we make sense of that grid? We use the chi-square test of independence. This is the absolute workhorse of clinical research for categorical outcomes in large samples. It systematically calculates whether the differences in the proportions we see, like the percentage of people getting sick on the placebo versus drug X, are just random noise, or if there's a genuine statistically significant difference. Basically, it compares the observed data we just collected directly against the expected frequencies we'd see if the null hypothesis of absolute independence were actually true.
The ultimate goal here? Getting that p-value to drop below 0.05. That means there's less than a 5% chance the observed clinical outcome was just a fluke of random chance. When a researcher runs the chi-square calculation and the result dips below that magic 0.05 threshold, they can formally reject the null hypothesis. They've essentially proven mathematically that taking the drug and surviving the disease are truly associated in their study population.
Now for section 4, the small sample problem.
Here's the catch. The chi-square framework isn't some magical, flawless tool that works perfectly everywhere. It actually has a very strict breaking point. What happens when you're evaluating a specialized pilot study where finding patients is incredibly hard? Say researchers are studying a super rare condition, like carcinoma of the gallbladder, where a clinic might only see 2 patients a year. Or what if they're looking for an incredibly rare but deadly side effect to a new medication? When your study pool shrinks, the standard math starts to fracture.
It all comes down to the number 5. The chi-square test relies on large sample approximations. This is the golden rule. If your sample size is so small or the adventure tracking is so unbelievably rare that the expected count in any single cell of your 2x2 table drops below the number 5, the math literally shatters. The continuous curve the chi-square relies on breaks down completely, yielding totally misleading probabilities. If a researcher ignores this and just pushes a chi-square test through their software anyway, they risk publishing entirely false claims based on mathematical errors.
So what's the fix? Section 5, Fisher's exact test.
To prevent a disastrously inaccurate analysis when your sample shrinks past that threshold, you have to pivot. Enter Fisher's exact test. Unlike chi-square, which estimates significance using a continuous curve, Fisher's calculates the precise, exact mathematical probability of obtaining your specific data configuration just by chance. This is a massive distinction. For large samples, estimating with chi-square is fast and accurate. But for small ones, we can't afford to estimate. Fisher's computes the hypergeometric probability, basically crunching every single possible way the data could have fallen to tell you if your specific result was a fluke.
This makes Fisher's the heavy hitter for small sample sizes. It's mathematically rigorous and absolutely vital for rare adverse event monitoring. If you ever see a trial with a tiny group of participants or an outcome that almost never happens, and they are comparing distinct buckets of categorical data, you should immediately check to see if they used Fisher's exact test. It ensures the integrity of the findings when data is scarce. But wait, there's actually one more massive assumption both chi-square and Fisher share, the assumption that your data groups are completely independent.
So the next time you see a headline, ask yourself, did they use the right test? Because here's a crucial distinction for advanced research. What if the categorical data is actually dependent? Say a study measures the exact same group of patients before and after an intervention, like checking if individuals successfully quit smoking after going through a specific behavioral therapy program. Because you're looking at the same people across a timeline, the observations are paired. In that scenario, standard chi-square and Fisher's tests are completely invalid. Instead, researchers must execute what's called the McNummer test, which is specifically designed to analyze paired nominal data to see if a significant shift occurred. At the end of the day, a clinical breakthrough is only as reliable as the statistical framework holding it up. By understanding the boundaries between continuous and categorical data, independent and paired groups, and knowing when to apply chi-square, Fisher's, or McNummers, you can look past the headline and right into the true mathematical heart of a study. Keep questioning the data, and I'll catch you in the next explainer.